Hello friends, welcome to the third video on this question with question code 102. Friends, I have already made two videos on this question in which I have done part A of this question through two methods. One is PMF method and other is CDF method. In part 1 video, I have discussed with PMF method, and in part 2 video, I have discussed with CDF method. So in this third video, I will be discussing the part B, that is minimum among x1 and x2, how to find PMF of minimum functions. So before I start the video solution, I will request everyone to go and watch the part 1 and part 2 video of this question. You can watch that videos in this I button. So those students who have already watched part 1 and part 2 video, they can easily understand this question that I will be explaining now. So let's see what is this function z2 is equal to minimum x1 and x2. So the given function is z2 is equal to minimum among x1 comma x2. So similar to maximum function, we can expand this function and write it as z2 will be equal to x1 when x1 is smaller than x2, and z2 will be equal to x2 when x2 is smaller than x1, and when x1 and x2 are equal, then z2 will be equal to x1, or we can either use x1 or x2. So in this case, z2 will be equal to either of these two. Either we can write x1 or x2. So now to calculate the PMF of z2, we simply need to calculate what is this probability. Probability that z2 is equal to some sample value small z2. If we can find out this probability for all the sample values, then we can easily find out what is the PMF. So this probability will be, from this definition of z2, we can see this probability will be equal to, for the first case, when z2 is equal to x1 and x1 is less than x2. This I am writing as first case, this is second case, and this is third case. So in the first case, this probability will be nothing but the probability. Here z2 is equal to x1. So here in place of z2 I am writing x1 is equal to sample value z2. So in the first case, this probability is equal to this probability, and when x1 is less than x2. So this is the PMF of z2 in first case. Similarly, we can write in second case, it will be x2 is equal to z2 when x2 is less than x1. Similarly, for third case, here we can write x1 or x2. It doesn't matter. z2 when x1 is equal to x2. So this is our first case now. This is our second case, and this is the third case now. If we can find these probabilities in these three cases, we can find what is the PMF of z2. So let's see what is the first case now. So the first case is case 1, probability z2 is equal to small z2 is equal to probability x1 is equal to z2 when x1 is less than x2. So this is the first case. From the definition of marginal PMF and joint PMF, we know that probability x1 is equal to some sample value x1 will be equal to summation over all sample values of x2, and joint probability x1 is equal to x1 and x2 is equal to sample value small x2. This is the relation between the joint PMF and marginal PMF. So applying this definition of marginal PMF here, we get this value. Applying it here, so it will be equal to summation over all sample values of x2, joint probability x1 is equal to sample value x1, small x1, but here small x1 is equal to z2. So writing here z2 and x2 is equal to x2, provided we satisfied this condition. So now I will include this condition over this summation. So instead of all sample values of x2, we can simply write all sample value of x2 which satisfy this condition. So such that all sample values of x2 such that x2 is greater than x1. Moreover, we noted here that here only sample value of x1 is z2. So instead of this x1, we can write z2 here. So it can be further simplified for all values of for all sample values of x2 such that x2 is greater than, here x1 is nothing but z2. So here x2 is greater than z2. Probability x1 is equal to z2, comma x2 is equal to x2. So this will be the probability that z2 is equal to small. You note it down here that this is nothing but the sum of all the joint PMFs of x1 and x2 such that x1 is some fixed value z2 and x2 is greater than that fixed value z2. So sum of all such joint probabilities will be this probability. Similarly, for case 2, we have probability z2 is equal to z2 will be equal to probability x2 is equal to z2 when x2 is less than x1. This we know from our previous discussion here. So similar to above discussion, you can write this will be equal to summation over all sample values of x1, probability x1 is equal to sample value x1, and in this case we will write here that sample value x2 is fixed and it is equal to z2, provided under this condition. So this condition I will write down here such that x1 is greater than x2. Since in this case only sample value of x2 is z2, so in place of this x2 we can write z2 here. So this can be further simplified to summation over all values of x1 such that x1 is greater than z2, joint probability x1 is equal to x1 and x2 is equal to z2. So this is the final result for our case 2. You can note it down here that this probability is nothing but the sum of all the joint probabilities such that x2 is fixed and x1 is greater than z2. Similarly, for case 3, probability z2 is equal to small sample value z2 is equal to probability that x1 is equal to x2 is equal to small sample value z2. So this is nothing but the case of joint probability that x1 is z2 and x2 is also z2. So this is our case 1, final result in case 1. This is the final result in case 2. This is the final result in case 3. So the overall probability that capital Z2 is equal to small z2 will be the sum of these 3 cases. So let's write what is the overall probability that capital Z2 is equal to small z2. So the overall probability that z2 is equal to small sample value z2 will be summation over all sample values of x2 such that x2 is greater than z2 from joint probability x1 is fixed and is equal to z2 and x2 can vary with sample value small x2 such that x2 is greater than z2. This is from the case 1 plus from case 2 summation over all sample values of x1 joint probability. In this case x1 can vary and x2 is fixed and is equal to z2. x1 can vary such that x1 is greater than z2. This is from our case 2 and last case probability x1 is equal to z2 and x2 is equal to z2. So now let's try to understand what each of this expression is graphically. Firstly, let's see what is this expression. I am writing this expression as A, and this expression as B, and this expression as C. You see, in the expression A, x1 is fixed and x2 can vary. How it can vary? It depends on this condition. So let's see what does it mean when x1 is fixed. Let's say this is the value on x1 axis. At this point x1 is z2. So let's say here at this point x1 is equal to z2. So this line here which goes parallel to x2 axis will be x1 is equal to z2 axis. So let me draw it here. So this line is x1 is equal to z2 line. So it will intersect x1 is equal to x2 line at point z2 comma z2. So let's write this point z2 comma z2 as point P. So x1 is equal to z2 means that point x1 can lie anywhere on this line. x1 is equal to z2 line. Now let's see what is this condition. x2 is greater than z2. So on this line we can see at this point P, exactly at this point P, x2 has value z2, and above this point P on this line we can see its value is greater than z2. For example, suppose this point is 2 comma 2. So we can see here on this line Above this point, its value will be always greater than 2. For example, here it can be 3, here it can be 4, 5, 6. It will be increasing. So its value, x2's value on this line is always going to be greater than z2. And below this point on this line, x2 value will be always less than z2. So both of these conditions, x1 is equal to z2 and x2 greater than z2, is satisfied by the section of this line x1 is equal to z2, which is lying above this point P. So only this section, that is lying above point P of x1 is equal to z2 line, only this section is the section that is satisfying both of these conditions. So expression A is nothing. So expression A, we can write it is equal to sum of joint probabilities of ordered pairs lying on the boundary I am calling this boundary as boundary B1. So all points lying on this line which are above point P is the boundary B1. So similarly for expression B, we can see that it is the sum of all the joint probabilities of ordered pairs such that ordered pair lies on x2 is equal to z2 line and satisfy the condition x1 is greater than z2. So let's see what kind of ordered pairs will satisfy these two conditions. So firstly, x2 is equal to z2. Since we have already taken that this point is x1 is equal to z2, so correspondingly this point will be z2 comma z2. So here on x2 axis, this point at this point x2's value will be z2. So x2 is equal to z2 is the line that is passing through this point and parallel to x1 axis. So let's draw this line. So this is x2 is equal to z2 line. So first condition is that all those ordered pairs which lie on this line, and second condition is x1 is greater than z2. You can observe here that on this line x2 is equal to z2, for all those points which are lying to the right of point P, we will always have x1 is greater than z2, and all those points which are lying on this line and to the left of point P, x1 is less than z2, and at point P itself x1 is z2. So this condition x1 is greater than z2 is satisfied all those points which are lying to the right of this point P. So the common region that is satisfying both these conditions is the region that is lying on this x2 is equal to z2 line and to the right of point P. So this boundary that is lying to the right of point P and x2 is equal to z2 line is the boundary that is satisfying this expression B. So I am writing this boundary as boundary B2. So expression B, we can write it is the sum of joint probabilities of ordered pairs lying on the boundary B2. So expression B is the sum of all the joint probabilities of ordered pairs that are lying on this section of x2 is equal to z2 line, only on this section which is lying to the right of point P. Similarly, we can see the expression C. So expression C is nothing but the joint probability of this corner point. Joint probability that ordered pair x1 x2 takes this corner point. So it is equal to the joint probability of at corner point. This corner point P. Corner point P. So if I combine all these three cases, you can see that probability Z2 is equal to Z2, small z2 is nothing but the probability that x1 and x2 lie on combination of B1, B2 and point P. So combining the boundary B1, B2 and point P, we can see that overall boundary we will get that I am going to draw here with red line. So this is the boundary that will determine the probability Z2 is equal to small z2. Since this red boundary is obtained by the combination of boundaries B1, B2 and point P, which is for case A, case B and case C, so the overall probability that capital Z2 is equal to small z2 will be equal to sum of joint probabilities of all ordered pairs lying on red boundary, this red boundary, which is the sum of boundaries of B1, B2 and point P. So this will be the total probability of Z2, where Z2 is minimum x1, x2. So this is the final conclusion of obtaining the PMF of minimum function. We can note here that depending on the value of Z2, where Z2 can take any value, the corner point P, which is point Z2, Z2, this point can vary. For example, if this value is 1, this point will be 1, 1. If this value is 2, so this point will be 2, 2. So we can see that depending on the value of Z2, we can have different boundaries in this x1 and x2 plane. So I will draw all those boundaries on next page. So let's see what are the different boundaries that we can draw for Z2 equal to minimum x1, x2 case for calculating the probability Z2 is equal to small z2. Since this small z2 is the sample value of random variable capital Z2, it can take any value depending upon the x1 and x2. For example, let's see what will be the boundary for the case probability Z2 is equal to 1. Suppose small z2 is 1. For that case, let's plot the boundary here, boundary condition. So for that case, we know the boundary will have corner at point P, which is 1, 1. So 1, 1 point is this. This is the 1, 1 point. So this is the boundary corresponding to this probability. From the joint PDF or PMF, we can sum up all the joint probabilities that are lying on this boundary and calculate this probability. Similarly, let's see what is the boundary for other case Z2 is equal to 2. So for this case, we saw the corner point P here is 1, 1. For this case, the corner point P will be 2, 2. So this is the corner point. So for this case, the boundary will be, so this is the boundary for this case when Z2, capital Z2 is equal to 2. Similarly, the examiner may ask for non-integer value. For example, Z3 is equal to 2.5 or 5 by 2. For this case, the corner will be at 2.5. This corner P will be at 2.5, 2.5. So the boundary will be, so this probability will be sum of all the joint probabilities that are lying on this boundary. So we can easily find out the PMF or probability in when Z2 is minimum function by simply drawing these boundaries and then summing up the joint probabilities lying on these boundaries. So just for better understanding and comparison with the maximum function, I am going to draw here. If Z2 is maximum for x1, x2, and we need to find out what is the probability that Z2 is equal to 1. I am going to draw here what will be the boundary to calculate this probability for maximum function. Here we have drawn what will be the boundaries to calculate this probability for minimum function. So with yellow pen I will draw what will be the boundaries for calculating similar probabilities for maximum case. So let's see for this. So similar to maximum minimum function, the corner point for this will remain same. So it will be point P will be 1, 1. But the boundary will be different. We saw in the part 1 and part 2 videos of this question that for this case the boundary will be, so to calculate this probability, this is the boundary for maximum function. You note down here for minimum function it is in this direction and for maximum function it is in this direction and the corner point will remain same. So similarly, probability that Z2 is equal to 2. For that case, the corner point will be 2, 2 and boundary will be, so this is the boundary, this boundary is the boundary that we will use for calculating the probability Z2 is equal to Z2 for maximum case. We will simply add up all the joint point probabilities that are lying on this boundary and that will give us probability Z2 is equal to Z is equal to 2 for maximum case. So for maximum case, we draw the boundary such that its mouth is open in this direction. Whereas for minimum case, we draw the boundaries such that its mouth is open in this direction. So this is how we draw the boundaries for maximum and minimum case. So let's now return to our problem that is given. So our given problem is x1 is uniformly distributed over -1 to 1. So it means that probability x1 is equal to small sample value, some sample value x1 is 1 by 3, where x1 belongs to set -1, 0 and 1. Only for these three values of x1 the probability is non-zero and is 1 by 3 for each case. For all other cases the probability is 0. Similarly, it is given that x2 is uniformly distributed from -2 to 2. So it means probability x2 is equal to some sample value small x2 is 1 by 5, where small x2 belongs to set -2, -1, 0, 1 and 2. Only for these 5 values of x2 probability is non-zero and is 1 by 5. For all other cases the probability is 0. So jointly x1 and x2 will have joint probability x1 is equal to x1, x2 is equal to x2, and this probability will be equal to product of marginal probabilities, because here x1 and x2 are independent random variables. So it will be equal to probability x1 is equal to x1 into probability x2 is equal to x2, where ordered pair x1 comma x2 is obtained by the Cartesian product of these two sets. So we can see here ordered that we can get 15 ordered pairs. First point is -1 comma -2. Second point will be -1 comma -1. Third point will be -1 comma 0. Fourth will be -1 comma 1, and fifth will be -1 comma 2. So in such way we can get 15 ordered pairs. These 15 ordered pairs I have plotted in this diagram on x1 x2 plane. So these are the 15 ordered pairs we can get for the joint distribution of x1 and x2. For these 15 pairs only the joint probability will be non-zero. For all other points in this x1 x2 plane the joint probability will be 0, and this non-zero probability will be equal to, this probability is 1 by 3 and this probability is 1 by 5. So this joint probability will be 1 by 50. So after drawing this joint distribution of x1 and x2 in x1 x2 plane, we can easily find out what will be the Pmf of Z2, which is minimum x1 x2. So to calculate the Pmf of Z2 we need to calculate what will be the probability that capital Z2 is equal to small sample value Z2. To calculate this probability we need to draw different boundaries that are possible in this x1 x2 plane for different values of Z2. Those boundaries are same that we discussed earlier with corner at Z2 comma Z2 and for minimum function. So let's see for such one case. For example, let's begin with case probability Z2 is equal to -3. So in this case the corresponding boundary for the minimum function will have corner point P at, its corner point P will be at -3 comma -3. On x2 axis here it is -3 and on x1 axis here it is -3. So this point here correspond to -3 comma -3 point. So the corresponding boundary in x1 x2 plane will be this boundary that I am going to draw here with yellow. So we can clearly see that there is no point out of these 15 points that is lying on this boundary. So this probability will be equal to 0. Similarly, we can see for all other boundaries which are not overlapping with these 15 points. For example, if we draw the boundary at this point minus 4 comma minus 4 point, so the boundary will be, so in this case also where the corner point is minus 4 comma minus 4, probability Z2 is equal to minus 4 is 0 because there is no overlapping point between this boundary and these 15 points. So similarly we can see if we keep on drawing these boundaries in this downward direction, there can be never be overlapping between these points and this boundary. So the first time the overlapping between boundary and these points will occur is when we consider the boundary with corner at minus 2 comma minus 2. So that boundary corresponds to probability that Z2 is minus 2. So let's draw the boundary for this probability. So it will be this boundary. We can see here in this case there are 3 points for which there is overlapping. So the sum of joint probabilities of these 3 points will be this probability. So this probability is equal to sum of joint probabilities of these 3 points. So here it is 1 by 15 for this, 1 by 15 for this, and 1 by 15 for this. So it will be 3 by 15. Similarly, the next boundary we can see that non-zero probability will occur when the next boundary will have corner at minus 1 comma minus 1. So let's draw that boundary out. So corresponding to this boundary, we will have probability that Z2 is minus 1 will be equal to sum of the joint probabilities of all the points that are lying on this boundary. So here we can see 1, 2, 3, 4, 5, 6. So the answer is 6 by 15. So next non-zero probability will be that when Z2 is 0. So the corner corresponding to this, the corner of the boundary will be at origin. So this is the origin. So the boundary corresponding to this probability will be, so this probability will be equal to sum of joint probabilities of these 4 points that are lying on this boundary. So the answer would be 4 by 15. So next non-zero probability will occur when Z2 is 1. In between 0 and 1, we can never draw a boundary here with corner on x1 is equal to x2 line which will overlap with any other point. So next non-zero probability will occur when the boundary in x1 x2 plane will have corner at 1 comma 1. So let's draw that boundary. So this probability will be equal to the sum of joint probabilities of these 2 points that are lying to the boundary corresponding to this case. So answer will be 2 by 15. You can see here that above this 1 comma 1 point on x1 is equal to x2 line, if I draw any other boundary for minimum case with corner on x1 is equal to x2, there will never be any overlapping between that boundary and these 15 points. For example, if I draw a boundary here for case Z2 is equal to, let's calculate this case, probability Z2 is equal to 3. So corresponding to this case, the boundary will have corner at 3 comma 3. So let's draw this boundary also. So we can see here this boundary and these 15 points, there is no overlapping. Similarly, for any value of Z2 which is greater than 1, we can see here, even if you draw for Z2 is equal to 2, for any value that is greater than 1, we can see here there will be never be overlapping between the boundary and these 15 points. So for all the values of Z2 which are greater than 1, the probability is going to be 0. So these 4 cases, this, this, this and this. So these 4 are the only non-zero probabilities corresponding to Z2. So this is the PMF of Z2. So now we will see a question which came in GATE 2020 on this minimum function. So let's see that question. So this is the question that was asked in GATE 2020 and it is based on minimum function. So here it's given that there are two tosses, toss 1 and toss 2. The output of toss 1 is labeled as random variable m and it can take values 0 and 1. Similarly, the output of toss 2 is labeled as random variable n and it can take values 0 and 1. Since both the tosses are pair, so the probability that capital M is equal to small m will be 1 by 2 for when an output is 0 and 1 by 2 when output is 1. Similarly, for random variable capital N, the probability that capital N is equal to small n will be 1 by 2 for both cases. It is also given that m and n are independent random variables. So jointly m and n will have the joint PMF which will be equal to the product of marginal PMFs. So the joint PMF will be the product of marginal PMF. So it will be 1 by 2 into 1 by 2. It will be 1 by 4 for ordered pair m and n, where ordered pair m and n is the Cartesian product of these two sets. First set is 0, 1 and second set is 0, 1. So there can be 4 ordered pairs in m and n plane. These 4 ordered pairs are 0, 0, 1, 0, 0, 1 and 1, 1. So these 4 are the possible ordered pairs that are jointly distributed in m and n plane. And the probability of each of these points is jointly 1 by 4. So in question he has asked about expected value of x, where x is minimum among m and n. So the expectation of x will be summation over all values of x into probability that capital X is equal to small x. So to calculate the expected value of x, we will need the PMF of x. So the PMF of x we can calculate here by drawing the boundaries corresponding to minimum function in this m and n plane. We can see from this diagram that first non-zero overlapping between the boundary and any of these 4 points will occur when we consider the boundary corresponding to x is equal to 0 case. So that boundary will be this positive m and n axis. So let me draw that boundary. So this boundary that I have drawn here corresponding to positive m and n axis is the boundary for which non-zero probability will occur, and it will correspond to case x is equal to 0, because here the corner point is 0, 0. So this probability will be equal to sum of the joint probabilities of these 3 points. So here for each of these points the joint probability is 1 by 4, so the sum will be 3 by 4. So next non-zero probability will occur when x is 1. For that we draw a boundary here with corner at 1, 1. We can see there is only one point, so corresponding joint probability for this point is 1 by 4. So here answer will be 1 by 4. So we can now calculate expectation of x. So this is the PMF of x. So we can calculate this will be equal to x value is 0. So 0 into its probability, which is 3 by 4, plus next value is 1 into its probability, which is 1 by 4. So answer will be 1 by 4. So here we will write 0.25 in our GATE exam. So I hope you have learned in depth how to handle minimum functions, and in GATE exam if you have understood all the approach that I have explained in this video, you can very easily solve such questions and get good marks in GATE questions. So I hope you will press that like button below this video and also subscribe to my channel for more such videos and in-depth analysis of GATE questions, and learn more and more concepts and get good rank and good marks in GATE exam. So thank you for watching this video and good luck for GATE exam.